Algebra 2, we're in lesson 20, found on page 98, and we're looking at the simplification of radicals. And then the second half, we're going to get back into linear equations, and we're going to find a line that's parallel to a line that's given, but we'll look at that and I'll show you how to do that in just a little bit. Well, let's start with the easiest of easy, okay? If we break this 16 down, and the root of 16 we know is 4. So we could also say that the square root of 4 and the square root of 4 equals the square root of 16. In other words, what's inside the root multiplied together can give us that number. An example they give you in your text is the square root of 10. There is no true root of 10, but we can break this down by doing a factoring. And if we divide that by 2, we get 5. So what we can do is we can basically put radicals on both of those and multiply them to equal radical 10. Okay, so we are putting those together. Okay, this is what's called the product of square roots theorem. And so if we multiply 2 in the root, we can still get a full root here. Okay, so on the top of the page, 99, it says this theorem can be generalized to the product of any number of factors. We say that the square root of any product of positive factors can be written as the product of the square roots of the factors. So what does that mean? Well, they give you an example where they give you a square root of 2 times 5 times 5. Well, 5 times 5 is 25 times 2 is 50. So we could also write this the square root of 50. So that's all we're basically saying, okay? 3 times, or the next equation or the example they give is the square root of, and then it's 3 times 3 times 3 times 5. So we can write that by saying 3 to the square root of 3 to the square root of 3 to the square root of 5. In other words, we're multiplying all these together and it comes up with the same thing. Okay, now what's the kind of problem we're going to get? Well, 3 to the square root of 50 minus 5 to the square root of 200. Alright, how do we get these two roots essentially to be the same? Well, we're going to have to rewrite these and demonstrate this. So you start by factoring. So we divide by 2 and we get 25, and of course we get 5 and 5. So really what we're saying for this expression is 3 to the square root of 2 times 5 times 5. Does that make sense? I got my 5 here, 5 here, this 5 here, this 2 here, and the 3 stays on the outside. So we're going to do the same thing for this one, okay? Alright, so I just factored it out. So we're going to say 5 to the square root of, and then we're just going to go in order. There's 2 times 2 times 2. We have 3 2's, and then we have 2 5's times 5 times 5. Alright, so now what do we do? How do we get to this spot? Okay, well, here's what we're going to do. Anytime you have two of the same number inside of the root, you're going to reduce that to just one number and multiply it by the outside. So these two 5's become 1 5, and we multiply it by 3, because anything inside the root, its root is only 5. So 25, the root of 25 is 5. So we multiply 3 times 5, which is 15, to the square root of 2. So what we did was we took this and we reduced it to only 2 in the root, and now we have 15 on the outside. Well, we're going to do the same thing over here, but over here we have something interesting. We have a 5, we have a 2, and So that means we can do is we can take 5 and multiply it by 2, which is 10, and multiply that by the outside, and guess what? We're left with 2. So we have 50 square root 2. Well, now we can do our problem because we have 15 to the square root of 2 minus 50, to the square root of 2, and we can actually make that happen, okay? Because the root now is the same. It's kind of like common denominators, except we have to have common roots. So 30 minus 15 is negative 35 to the square root of 2. That's our answer. Okay, so these problems are not that difficult. That's adding and subtracting. Of course, if we added it, you'd just have a positive. It would be 65 instead of negative 35. So again, not too difficult. When we multiply them, okay, which is the next problem, 3 to the square root of 2 times 4 to the square root of 12 times 2 to the square root of 3. Again, what we're doing is we're multiplying what's inside the value. So 2 times 12 is 24 times 3 is 72. So 72 is on the inside. What's on the outside? 3 times 4 is 12, times 2 is 24. And then we can factor this, and then whatever we apply to the factor we can multiply out, and we'll get 144 to the square root of 2, because if we divide this, we're going to get 36, or divided by 2. We've got by 3, and we've got 12, and 3, and we've got 4, and then 2 and 2. And so again, we're going to take these two and these 3. 2 times 3 is 6, times 24 is 144 to the square root of 2. That's our answer. Okay, so that's how you do those kinds of problems. Alright, so now let's get into 20b, which is dealing with the line parallel to a given line. Alright, so as we look at this, we're going to notice a grid or a parallel lines, okay, and you're going to see these in your textbook, and I'm not going to draw every single grid because we can solve this algebraically, but you're going to see a line that comes off something like this, and then there's another one that's like this, and another one like this, and basically they all each have an equation, and they're supposed to be perfectly parallel to each other. And what we're going to do in our example question is we're going to find an equation of a line that is supposed to be exactly parallel. So they're going to give us a line, and then they're going to say, okay, here's the equation of the line. It is 2y minus x equals 2. Okay, we have to change this into an equation that is y equals mx plus b format. And so how do we do that? Well, if it's 2y minus x equals 2, we're going to move this x over here, and it's going to be 2y equals x plus 2. We divide by 2 all of these, okay? Y now equals 1 over 2x plus 1. So this is the equation that we're going to end up trying to use to solve for our parallel line. And then in 20.4 on page 100 it says it passes through the point 3 and negative 1. There's our coordinate, okay? So we need to use 3 and negative 1 and this equation in order to solve for this problem. Well, y equals 1/2 x plus 1, and then we have 3 and negative 1. We can solve for this new problem. Okay, we can actually solve for this. So we know that if we're going to get a parallel line, it still has to have the same rise over run. Okay, so we're going to leave that alone. but we do know the x component. So we can actually substitute 3 for x and solve for this. And we also know the y component, which is a -1. Okay, so we want to know what the new intercept is going to be. Okay, so if we have a coordinate, and let's say that let's graph y equals 1/2 x over 1. Well, a positive 1 would be right here, and rise 1 over 2, 1 over 2, 1 over 2. So we would have lines that would be something like this. Okay, we don't know what our new intercept is going to be, but we want it parallel to this line. So either it's going to come down here or it's going to be up here, but we know it's going to be rise over run is still up 1 over 2. So we're still going to have these lines, or down 1 and over 2. So what do we do with this? Okay, so our new equation is -1 equals 1/2 times 3 plus b. We got to find b by itself. Okay, so in order to do that, we're basically saying that -1, we can look at that as 2 over 2 equals 3 over 2 plus b. Okay, let's subtract 3 over 2, subtract 3 over 2, and b now is going to equal 2 over 2 minus 3 over 2, which is going to be a -5 over 2, because we have a 2 here and a 3 here. Now you're like, how did you go from 1 to a 2 over 2? Well, because you have common denominators, I just made this 1 equal to 2 over 2. That's how I came out with this. So now our equation, since we solved for b, we know what the y-intercept is now. Y is going to equal 1/2 x. We know that that stays the same, minus 5 over 2. Okay, so this is our b-intercept. And again, we don't need to graph that. We could, but we can solve that pretty easily and come out with the equation. All we're looking for is the equation of a parallel line. So we're using the coordinates, our initial linear equation, and solving algebraically for b. All right, if you have any questions, you can ask me, and we